it's a pleasure to see everyone here and to have Gil Refael here from Caltech, who's going to talk about, I think, Floquet phases and topological physics. So Gil did his PhD at Harvard with Daniel Fisher and Eugene Demler. Actually, Gil was Eugene's first student, I believe. Okay, I see. So there was a very high bar after that. Every time Eugene writes a recommendation letter for a student, there's some kind of reference to Gil, good or bad. So after that, Gil went to UCSB, to KITP, where he worked with Matthew Fisher. And then he moved to Caltech, where he's been ever since. I think Gil has won a bunch of nice things like Sloan and Packard Fellows, and since now he's the Taylor Lawrence Professor of Theoretical Physics. So it's a pleasure, Gil, and please explain us about topological physics.
Thanks, Luis. Thanks, Eugene, for inviting me. Pleasure to be here. What do I say? Oh yeah, so I wanted to clarify. So I think I was Eugene's zero student in the sense that when I was working with him, he was not yet a professor,
right,
but about to be.
Exactly.
At Harvard. So I would count. So he agrees that I was the zero student, and Daniel Podolsky was the first one. But, I recruited Daniel. The other statement. So Taylor Lawrence is the benefactor of the chair that I have, and he used to run Raytheon's missiles division, but not anymore. But back in the day, I used to say, well, so you know this is my benefactor, so think twice before you ask a question. But he's no longer in charge of the. I guess the equivalent is. I guess the joke I should go to Obama. I guess in one of the press, the White House press talks, the White House press dinners, right? Yeah. He gave a talk and he said, "For those of you who are trying to date my daughters, I have 2 words for you: kilograms." Anyway, so back to our business. So it's really a pleasure to be here. I wanted to talk about kind of a reviewish talk about things that I've been doing in the interface of dynamical systems and topological physics. So I'll start with an introduction, work that I've done 10 years ago, 5 years ago, and then some work that I'm engaged in right now to give you a flavor of where things are going. I intend this to be educational as I can, so ask me questions in the middle, in which case I won't get through all my slides, no big deal. All right, so I'll use the pointer on my computer. Does this work? Okay, so, okay, there we go. So first order of business is, why is topological? So I'm sure you've seen a lot of talks about topological, and usually they go something like this. It's about invariant features of shapes. So to drive the point home, think about taking a piece of paper. You can wrap it around to make a cylinder, no doubt there, but now you face 2 choices. If you want to make a closed surface, you can either close the 2 sides of the cylinder into a lollipop, which is equivalent to a sphere, or you can connect the 2 sides of the cylinder around, and then you get this universally appearing picture of a torus turning itself into a mug, turning itself back into a torus, indicating that a shape, topological properties of shapes are the number of holes in them. And the mug and the torus are topologically equivalent, so depending on whether the speaker likes bagels more, you see this picture, or donuts more, you see this picture, and indicating equivalence of topology. So the donut and the sphere are not equivalent. And you can make a spherical donut, but I don't think you can make a spherical bagel. So maybe that's not completely equivalent.
Bialys?
What?
Bialys?
Bialys, spherical bagel?
Well, same topology.
Okay.
No.
I'm not familiar with those. I thought donuts, I mean, there's Boston cream, right? So, but in physics, what's the examples of topology in physics? Many examples. The ones closer to my heart. So vortex physics, maybe the most ubiquitous example. So weather phenomena clearly dominated by vortex physics. There's very big difference between a clear day with a wind blowing in one direction, and the hurricane, which has a topological defect in the wind formation. The wind is a circle. If you want to get rid of a hurricane, you can't really stop it. You can't nuke it. The only thing that the hurricane can do to stop is do landfall, where everything is damped uniformly. So literally speaking, if you want to kill a hurricane, you need to take that hole from the middle of the hurricane and take it away from the storm. So that gives it topological stability, which is unfortunate for us. In condensed matter physics, superconductors have vortices in them. Those are like hurricanes of electrons that surround magnetic flux. And I would say they wreak havoc on the superconductor, but no comparison to what the hurricane would do. And those vortices are responsible for dissipation in superconductors. And a lot of us are familiar with either superconductors, vortices, or dissipation. Before continuing, I want to say that other professions also have opinions about topology. For instance, you'd be surprised, but archaeologists seem to care about topology. For instance, here's an example of a Roman Empire era jug. It has an Euler index of 1, or at least the number of holes is 1. There's a genus 1. And you can see that it costs $12,000. And you can see a genus 2 Roman era jug. And you can see that there's no price mentioned, which means that genus 1 is $12,000, genus 2, priceless. Wine enthusiasts seem to also have their opinions. So if you have a nice carafe, you can have a genus 0 carafe. You can have a genus 2 carafe. And special wine scientists also developed the genus 1 carafe. So you can see that clearly is important. Yeah, it's just one hole, right? It's a cylinder. There's also the body, the body art aspect of topology, which I'm not going to dwell on. So what is topological in physics when you say topological phases? So the flavor of topology that I was engaging with has to do with electronic spin. So remember the spin half, this thing that they teach us all the time about? If we want to describe it in Schrodinger equation, we need to write a two-tuple spinner, right? And we can parameterize the two-tuple spinner in terms of the polar angles, theta and phi, the angle to the z-axis and the angle of the projection of the xy. And each theta and phi gets a representation of the wave function. It's cosine theta over 2 sine theta over 2 e to the I phi. You know, when we were kids, we were reading this in Stephen Hawking's book, probably about, rotating around the circle, and you get a -1. It's all in there. That's the star of this talk. The spinner that has a dependence on the direction of where the spin points. You all remember this representation? I find that I need to remind my students of it every once in a while. Spin can wind, just like a velocity field. So let's see how that happens. So in the context of the spin winding, we can talk about the one-dimensional topological phase. So let's construct a one-dimensional topological phase. Think about the wire and make it spin orbit coupled. What do I mean? So we all know about p squared over 2m for particles. Let's add to that another piece, which is spin, so sz dot with the momentum. In fact, let's forget about the p squared. Let's just have that. Small momentum, that will be dominant. So if you think about this wire, and you think about the spin up and a spin down would be moving in the opposite direction, right? So linear Hamiltonian means constant velocity, but the group velocity for spin up and spin down is opposite. Spin up electron will be moving to the right, spin down electron will be moving to the left. It's possible that I got the sign right, but don't call me on that. So the spin, so I can reverse that and say that an electron moving to the right, the ground state for that will be spin down. Electron moving to the left, the ground state of that will be spin up. So that's a momentum. So, and I want to emphasize this is like a momentum dependent magnetic field. That's crucial. Now in real life, there are no continuous spins, continuous wires. Every system is quantized in some way. Wires are actually collections of atoms in a crystal. So let's make the wire into an array of atoms at some distance a. And we know that in that case, the lowest band will have highest momentum will be determined by pi over a. Instead of p squared, the Hamiltonian would have cosine of p. And instead of a dispersion that's quadratic, we'll get a cosine. Sorry, where's my marker? Yeah. We'll have a cosine energy versus, sorry, energy would be cosine of momentum. There will be higher bands that will extrapolate into p squared, but we don't care about them anymore. And now in this band that stretches from minus pi over a to pi over a momentum, you can have a spin that circles all the way around the xy plane. So if so in this case, momentum is periodic. So you can think of momentum as being an angle. And that's a little slow with the marker. Then I can use. There was some laser pointer here that I can use. There we go. Right. Okay, that's easier, but the Zoom people cannot see it. Anyway, so momentum becomes periodic within this band, and the energy is a function of e to the IP, right? So that's really the variable that gives you the properties of the band, which means that momentum becomes kind of a root of unity that can circle in the complex plane around the origin. In other words, the Brillouin zone is a periodic object in momentum. Spin can be a function of that momentum. The momentum is parametrizing a circle. The spin can wind around it. So here I'll write an extension of the model that I had before, the SD times P. Let's write something else. It's completely made up. But you can imagine a spin orbit model such that the Hamiltonian is Sx times cosine of the momentum plus Sy sine of the momentum. For a given momentum, this looks like a magnetic field in some direction on the xy plane. And as a function of momentum kind of laid down on the table, this is what it looks like in the bottom. Just to drive the point home, if I write these directions of spin as a function of momentum, but parameterize on the circle, right, from minus pi to 0 to plus pi, it makes a vortex. That's the topology in the spin, which lives in the momentum space. Now you can see spins, so particles that move slowly in the right will have momentum over here, slope is very small, the spin will point to the right, and we can go around the Brillouin zone, going to faster and faster electrons, then slower again at the edge of the Brillouin zone. And depending on the motion of the particle, the spin is pointing elsewhere, and it wraps around the circle. So in the same way that the number of holes in a shape is invariant under squishing it, punching it, etc., the number of times that a spin like that wraps around the momentum torus is also constant. You know, the spin can wrap 0 times, 1 time, 2 times, etc. As long as the spin is not allowed to point in the z direction, just confined to the xy, there's a winding number. Questions so far? All right.
Why is it necessary that it completes full circle? Why cannot you imagine a situation when it does not come back?
Because the Hamiltonian is continuous. Yeah. Yeah, the wave function has to be single. Well, it can be single valued with a jump, but then it will be discontinuous in momentum. So I think that can only be with the long range Hamiltonian.
Always the case.
In condensed matter, it's always the case that it's continuous. We can discuss later if we can construct counterexamples. Certainly, the counterexample I think will require long-range interactions, long-range hopping. But in any local Hamiltonian, this will be the Fourier transform of the Hamiltonian will be a continuous function of momentum. Yeah.
Sorry, so what you are saying is that this Hamiltonian is allowed by the existing symmetries, correct? Whether or not it actually exists is a separate issue.
Correct.
But you perhaps as also assuming everything allowed by symmetry does exist or something.
Correct. Unless it's really good, in which case it's probably forbidden by the rule that can't have. Why is it no free lunch? So barring the no free lunch, yes. And this thing does exist, but it took a while to engineer it.
So everything you're considering now is living in 2 dimensions as well, is that right?
Right now it's 1D.
Oh, 1D, just 1D.
1D. So the
So
momentum in
is-
1 dimension is limited by the first Gil-Refael zone,
Okay.
which means that, so you can think about, so what do I say? So it goes from minus pi over a to pi over a lattice constant.
Mhm.
You can think of that as an angle.
Mhm.
And because the wave function is periodic in momentum for the first band, then you can think about that momentum living on a circle.
Thanks.
And that's why it's a winding. Otherwise, it will be more complicated. Sure. So yeah, it's the same question. Like it's like taking a wire and closing it and laying it down over something with a hole. So what kind of indices can you make out of that? So I think for that you can only make winding. Like how many times does your knot go around the stick? Yes. Other questions? So it turns out that if you take this Hamiltonian, and instead of, for the experts amongst you, I'll say that instead of taking spin, you take a combination of spin and particle Hall coordinates. So just a small transformation of this Hamiltonian to fit superconductors, what you get is the Kitaev model. So a p-wave superconductor with spin-orbit coupling will be a realization of that model. So here's Alexei Kitaev. Looks like some kind of an important event.
Yeah, he has a Getty Images too.
Things I can't make out the words in the back.
I guess
Mine
then
is
you,
what SOC stands for.
What?
I forgot.
Oh,
what
the
SOC
spin-orbit coupling. Spin-orbit coupling. Spin-orbit coupling. Yeah, I think that's the breakthrough prizes. Anyway, so he came up with this model many years ago, saying that there will be Majorana fermions in a p-wave superconductor that's spin-orbit coupled. And then he proceeded to write, although I think this model is the correct way of doing Majoranas, I don't think there's any chance of it being realized in reality, in nature. But after a lot of twists and turns, we think that we can realize this in reality, but I don't want to discuss. I'm not going to discuss Majoranas too much. But the upshot that I wanted to say is, yeah, spin-orbit coupled superconductor, according to Alexei, will give you Majorana edge modes, which then could be used for topologically protected quantum computation or quantum memory. So you can ask me about that separately. I will stay away from Majoranas right now, but I'll move on to two-dimensional topological phases. So two-dimensional topological phases, we have 2 dimensions of momentum. So now it's really a torus. We have a sheet that's a square that's periodic in the 2 directions. If you want to write a Hamiltonian along the lines of that wrapping Hamiltonian, I'll write the following thing. Px times sigma x, py times sigma y. So far so good. But then a z component that starts off being 1 and ends off at large momenta being -1 or minus infinity. Now the question of topology in 2 dimensions would be, how can you wrap a 2-dimensional sheet on the Bloch sphere? What is the Bloch sphere? Is that unit sphere where the spin can point to those theta and phi that I showed you in the spinners before. Okay, so let's look at this Hamiltonian and figure out in which direction the spin points as a function of momentum. We can start in the center of the Polariton zone. Okay, let's do it in sequence. Okay, we start at the gamma point. The spin wants to point up, but because these things are 0 and we only have this 1 sigma z. As we increase momentum going further and further away from the center of the Polariton zone, the spins start taking over the northern hemisphere. And if the phase is topological, as this Hamiltonian is, as we go to higher and higher momenta, this term eventually will change sign, and the spins will take over the southern hemisphere. And at very large momenta, the z component will be dominating and negative. So at very large momenta, the spins will point in the southern pole of the ball sphere. Altogether, we got a wrapping of the sphere, and that wrapping implies that this is a Chern. This Hamiltonian describes Chern insulator. It has an anomalous Hall conductivity, which is quantized, just like a lambda level. This is the Bernoulli-Hughes-Zhang Hamiltonian, at least one half of it. To be honest, again, there's always a crystal, never a continuum. So for a crystal, we'll have to change px to sine px, py to sum py, and the p squared into cosine px, cosine py, but everything works in the same way. This is the Bernoulli-Hughes-Zhang. All right. So I mentioned that this has anomalous Hall conductivity, and I would like to spend a slide explaining what it looks like or where it's coming from. So we all remember, I hope, how things move in a magnetic field, in a B field. Looks like this, right? Velocity cross magnetic field. Then you get the sign of E right, so that it will be the right. But now if you have Berry curvature, you get the dual of this equation of motion for real space. Namely, instead of dp dt, or in addition to dp dt being b cross v, you also have velocity equals, well, group velocity, familiar friend, plus Berry curvature cross the force. Just like magnetic field cross the velocity, we change r to p, we get this Berry curvature cross the force. What is this Berry curvature? So just like a vector potential, we can define a Berry connection, which is how much does the wave function, the spinor wave function of an electron moving with momentum p changes to the function of momentum. If you take a curl of that in momentum, that's the Berry curvature. I'll repeat something that I was describing to the students earlier. If you think about this, this is how much phase a wave function will accumulate as you make the particle change its momentum continuously. But that's the same like a magnetic field, right? The vector potential is how much phase an electron accumulates as you drag it in real space where there's a non-zero vector potential. The curl of the vector potential in real space is the magnetic field. The curl of the Berry connection in momentum space is the Berry curvature. Now here's the Bernoulli-Hughes-Zhang Hamiltonian, or more like it, this is the Berry curvature mapping of the Hamiltonian that I showed you before. There's a lot of Berry curvature in the center, in the gamma point, not so much in the edges. It integrates out to be constant flux. And now, if we apply a force in the x direction and we drag an electron from left to right, every time that it goes to the Berry curvature, high Berry curvature area is going to move perpendicular to the force. Let me repeat this because this is not a simulation, but rather a PowerPoint animation I worked hard on. So if we didn't have Berry curvature and we pull an electron with the force, and the force is not large enough to make the electron jump bands, it's going to do Bloch oscillations. It's going to move forward and then backward and then forward. And overall, the amount of work done on the electron by the force has to be zero because the electron does not have an energy bandwidth to absorb energy from the force. Right, so it has to end up in the same place so that the force does not do work on it. Yeah.
You may have said this, but are colors the magnitude of omega?
Yes, over here.
So colors are the magnitude of the curvature.
Exactly. So bright is high curvature. Right. Right. So as I do this animation again, you'll see that the particle goes back and forth on x, not accumulating any displacement. However, perpendicular to the force, well, no problem with energy conservation. It can go as far as you want. And because of this Berry curvature, the particle will indeed go every cycle in the same direction, accumulating y displacement. So that's anomalous Hall conductivity. Hall conductivity goes perpendicular to the force. Anomalous, no magnetic field. Questions? All right, so to wrap up the introduction, I wanted to say that this two-dimensional topological insulators were actually achieved, again, through the insights from Andre Bernovic, Taylor Hughes, and Shusheng Zhang, and Lawrence Mollenkamp expertise on cadmium telluride, mercury telluride heterostructure. They show that when you take the cadmium telluride, mercury telluride sandwich and make the mercury telluride layer thick enough, you go from a boring semiconductor, so insulating in the bulk, into an interesting semiconductor with edge states wrapping around the sample. You go from a boring semiconductor in weird pastel colors to an interesting semiconductor with spin-up electrons going on the edge in one direction, spin-down electrons going on the edge in the opposite direction. And that was a great discovery of two-dimensional topological insulators. This helical motion, this chiral motion of electrons, gets its interpretation in the Los Angeles area using freeways. That's the only way we can think about things. However, this cannot be a Los Angeles freeway because it's empty. The one way is spin up, the other way is spin down. The question of what you can do with this, maybe spintronic devices, maybe dissipationless leads, Majorana fermions, but we're not talking about those for quantum computing. This is all still on the table. Not so much progress actually done on that. It's an amazing material without so many applications yet. So that's open. My point is that you can take this idea and combine it with light. Take a semiconductor or a topological insulator or a topological material of a different variety, shine light on it, and new things can emerge. Maybe you can induce topological behavior where there wasn't any. Maybe you can make topological photonic states. You can get new paradigms for infrared detection, for far infrared detection. And you can also get new paradigms for photonic control, which is the thing I hope to get to. But in any case, turning on the light makes everything better. That's the point of the talk.
I have a question.
Yeah.
What kind of lifetime do you get for the spin population in your topological insulator? So I mean, like when it's powered, how long do you get the spin isolation moving in the continuous?
So it's not, what I showed you so far, it's not powered, it's in situ. So that's the material.
So those spins stay polarized for an indefinite amount of time.
Going one way polarized up, going the other way is polarized down.
For however long?
It's a good question. So in principle, if there's no time reversal symmetry breaking, forever. Forever. But that should not surprise you. Like if you have a wire, you have right movers and left movers, right? Right movers move right, left movers move left, forever. It's just that in this case, one is spin up and the other is spin down. Because there's no time reversal breaking, they cannot scatter into each other. So any scatterer that cannot reverse the spin cannot change the direction. That's why the application to dissipationless leads is appealing. However, it's a one-dimensional electron gas. Going into such a state actually has an intrinsic resistance of like 6 kilo ohms or 6 kilo ohms, 4 kilo ohms. Just unless you do something special. Yeah. But yes, forever. That's really cool. Forever. But that forever turns out to be tens of microns. in Lawrence's experiment, it was tens of microns. Hundreds of microns, I can't remember. Yeah, other questions? Okay, great. So first thing I wanted to show you is how can you take a semiconductor that's boring and turn it into a topological insulator just using light. With that, I would like to acknowledge my close collaborators, Nate Lindner and Victor Belitsky, who were partners in crime in this first work on the subject. And before I continue, I want to say that Oka and Aoki had similar idea around the same time, or even sooner, thinking about graphene-driven, basically polarized light. Okay, so let's start with a non-topological two-dimensional band. The spin as a function of momentum is pointing mostly in the northern hemisphere. Definitely not down. It starts in the z direction, it ends up in the z direction. Not topological, no wrapping. But now let's shine a laser light on it. That produces a resonance ring between the valence and conduction band. And I'm drawing it over here. Let's draw a cut with a spin direction in the bottom and in the top band. They're opposite. And here's the ring of resonance cut. We like doing a rotating wave transformation where we change the energy of the top band by the amount of the resonance to make the Hamiltonian time independent. On PowerPoint, it's very easy to show. Here, we're removing some energy from the top band. And we get a ring of resonance over here. Quantum mechanics makes the resonance be an avoided crossing. And we end up with this new dispersion because of the light. Now check it out. So this starts looking like a volcano. I know there's a natural disaster theme to this talk. Sorry about that. So in this new valence band, the far away states, the large momentum states, they're the same states as in the original valence band with spin pointing up. So now the crater is actually the bottom of the old conduction band with spin pointing in the opposite direction. If I'm lucky, and we did things right and we use circularly polarized light, the spin in the ring of resonance, it has to point in the XY direction pretty much, is going to wrap around the equator. And we know how to do this. Circularly polarized light, sorry, what do I want to say? Two things. In this case, we used light with a magnetic field in the Z direction that takes advantage of the XY components due to the spin-orbit coupling to create this resonance in such a way that there's no vanishing point around the circle. And that gives us the topological insulator, or at least the band structure of topological insulator. We can look a little bit under the hood. So if we think about tau matrices, like Pauli matrices, but in the space of valence versus conduction, here's the energy of the bands, epsilon p, either plus or minus, that's conduction valence bands, minus omega over 2, that was the squishing the two bands together in the PowerPoint, times tau of z. But now the light produces a matrix element between the valence and conduction band.
Why did time dependence disappear?
Because the light produces a hopping from top band to top to from what do I want to say? Lower band to upper band, right?
But also from upper to lower.
No, what I want to say is something different. So if you look at the matrix element of the light, right? It has time dependence, right? But it connects low band to upper band, and vice versa. Right, but with opposite, the e to the I omega t becomes e to the minus I omega t as you reverse it by the summation conjugate. Now, what you do is you do a transformation that changes the energy of all the conduction band by omega. So it's a unitary
because in
transformation.
your crystal there is this translation thing.
No, it's not a translation. It's just you
But
say.
if it
No,
wasn't
you
for
just
a
dress.
crystal,
You just dress all the wave functions in the conduction band with an extra e to the I omega t, which I'm allowed to do.
Or call it the Floquet Hamiltonian of the.
So I had the Floquet Hamiltonian. I can solve it, but I can also, in this level, I can do a transformation that absorbs the c to the I omega t in one of the bands.
I'll have to trust it. That's okay.
But it's a legit
Okay.
unitary transformation. There's one class of states. I say, oh, let's change their energy, but that means that the creation and annihilation operator will be winding in time. But the only place where this winding will not be cancelled by a c
You
dagger
can get
c.
rid of it. It's less limited.
Not only do you get rid of it, that's the transformation that gets rid of the time dependence. And instead of having a ring of resonance with the light, so maybe I'll say it because it's on my mind. You see this Hamiltonian? You see this dispersion? The ring of resonance is due to omega energy coming from the light, right? So we have a time-dependent Hamiltonian. The light is the time dependence. It can produce transitions with energy differences that are omega. I can do a transformation that will change the energy of this. It will reduce this down, but now that same transformation will take away the time dependence from the light, and what used to be a time-dependent resonance becomes a time-independent resonance of states in the same place. So you can see that it's equivalent.
Mhm.
Thanks. Other questions? All right, so what I wanted to say is that there's this matrix element that the light gives that connects the two bands. That's like a tau x tau y component. So there's a complex number g as a function of momentum that multiplies this tau x and tau y real part multiplies tau x, imaginary part multiplies tau y. So what I need to do in order to get a topological phase is take this G, which is the matrix element of valence to conduction, ask what it is at the resonance ring. The resonance ring is in px, py plane. Here's the resonance ring. This G is a complex number. It can point in the real axis at px, py equals 0, then change to be like 1 plus I, change to I, minus 1 plus I, minus 1, etc., such that G wraps around the origin of the complex plane. That will give a topological phase. And we know how to do that. So spin orbit coupling together with the sigma z magnetic field light of the light will give you exactly this winding. So a combination of this winding and the spin going from up to down as a function of the absolute value of momentum gives you a wrapping of the Bloch sphere, as I showed. We can simulate that. So full wrapping in tau space, but it doesn't matter where the wrapping is. As long as you have a wrapping, you can get rid of it. So here's a simulation. We took a square lattice in 2D. We connected it in one direction, so we have an edge along one direction. It was the same model that I showed you before, but not topological. We shine light in the sigma z direction. Because of the sigma x, sigma y components of the Hamiltonian, this produces a new band structure with a new band gap, like this volcano. But the numerics gives you these edge states, which are the hallmark of a topological phase. What are those edge states? Propagating chiral states on the two sides.
This is all theory, right?
Oh yeah, I'm a theorist.
Okay. You say we shine light, whatever.
Yeah, I mean, come on, I have ambitions. So I also, look, I have a laser in my hand.
So you do shine light.
I do shine light. But this is the theory. This was the theory. This is an example of a Floquet topological state. But there is an experiment. So Andrea Cavalieri actually made an experiment recently. And he did pretty much this. He took a sheet of graphene, shined infrared circularly polarized light on it, and checked the Hall conductivity as a response to a pulse that was going through the switch. And what he showed is that you have a sigma xy response when the light is on, none when the light is off. It's consistent with what Oka and Oki and we were saying. Just to explain one thing to the experts, when you shine light, you can have a second order response that looks like DC. Namely, in second order, you get amplitude squared. That's what people use for optical lattices to trap atoms. That's not really, it's okay, but it could be understood as a time-independent Hamiltonian. At the same time, so that would give you a factor quadratic in the amplitude. At the same time, direct resonance, like what I was describing, gives you linear effects in the field of the light. And Andrea checked both those effects on graphene. Similarly, Nuggetic early on showed that by shining light on topological insulator surface, you can also separate Floquet bands that emerge, which are expected to be topological. That was an example of this physics, but without transport to support it. So that was the first paper. It was groundbreaking, but not conclusive. Yeah.
So when you make the volcano, I guess the farther they make it, the topological gap or whatever also goes up. So where does it fall apart?
It doesn't have to fall apart, but at some point you can have a phase transition out of the topological phase. So there will be a phase diagram, and it is true that I think if the drive is too strong, you might lose some of the properties. But I did not investigate that part. Usually people are concerned with how strong of a light can you give, not what if the light is too strong. It's an interesting question, so I wish I had. Yeah, other questions? Yeah.
So with the light you're using like a laser, right? Or you would use a laser if you're an experimentalist. Is then the whole flake or graphene or whatever topological insulator you have, is it all topological, or is it only where around you're shining the light?
Only where you're shining the light. And you know, the numerical example that I gave had the magnetic field polarized in the z direction. I have to say, for theorists it's great. For experiment, it kind of sucks because magnetic fields of light are fairly weak. However, it turns out that so we calculated this for a quantum well type of device, mercury telluride, etc. There you can use the circularly polarized light from above with the electric field in the XY plane, and use the electric field to produce this band mixing, and that's very strong just because the electric field in light can be very strong relative to the magnetic. So this was the kind of beam that was used here. So you need a circularly polarized beam for that. Wherever the beam is, it will be topological place. Yeah.
Could you instead use a helical beam that has orbital angular momentum instead of spin angular momentum?
Yeah, that's a great question. I think Daniel Podolsky looked at this question. And I think what you end up with is, but there's interesting physics in that. You get a vortex state, I think. So you get a place where the band actually, when the gap vanishes, you can have quantized states there, possibly at zero. So kind of like vortices in POS superconductors supporting Majorana. So there's interesting physics coming, I think, from that. So he was looking at what happens when the phase of the drive winds in space. And that gives interesting. So we still need.
Field can also wind.
So I don't know whether it's it can be instead of topological, I don't know if it can be like, what do I say? I don't know if it can replace the circular polarization, but when you put that on top of the circular polarization, it does interesting things.
If light is focused, you get spin orbit coupling in the light anyway. So
Oh, it's a question of whether the G does what we want it to do. You know, it may do something else. It may vanish at some moment. How am I doing in time actually? Okay, so I'll take 15. But other questions? All right, so one question that I often get, or I often did get when I talked about this in seminars, is aren't I concerned about heating? You know, what I'm describing is I'm taking a quantum well, a semiconductor, shining a circularly polarized light on it from above. It makes a band gap, but it also makes a mess. It heats up. There's a separate line of work that we can do and have done on how you can stabilize a thermal-like state with this kind of irradiated material. I don't want to talk about that. But it did stimulate me to think whether we can do the same kind of physics with just a single photon. That way, instead of shining light and making a topological edge state, we shine just one photon that then creates an exciton in the material, that then creates a photon. And this oscillation between photon and exciton can propagate together along the edge as if it's the edge state of a topological insulators. Now, this is a very appealing thing to pursue because so a particle-hole pair, so an electron gets excited from the valence band to the conduction band, that's called an exciton. Piece of light is a photon. Together they make a polariton. And if it's topological, it would be called a topolariton. I thought it was a great name for a paper. But apparently I'm the only one who can pronounce like this this 5-syllable word, so it didn't catch up as much. But I'll tell you the physics anyway. So here's how it works. So it turns out that everything that can, in principle, be a topological Floquet, so it can also have this topological polariton mode. This is how it works. So how do you make a polariton? You can have excitons. Those are particle-hole bound states. You have a quantum well, it has a valence band, conduction band. You can excite an electron from the valence band, waiting for it to appear, there we go, to the conduction band. They have to be co-moving, they can propagate together in the quantum well. No problem, it has a dispersion. There's a gap, there's a dispersion. Photon, well, how do you get a photon? We all know how to get photons, but in this case I want to have it between two mirrors. So you can have a field of light propagating between those two mirrors. At high momentum, it will move with the speed of light. At low momentum, there will be a small gap because of the quantization in the z direction. Photon. Now, photons and excitons are both bosons. So you can put them in the same graph and let them hybridize. So I have this quantum well inside of this mirror in its optical cavity, make them hybridize. So here's the photon, here's the exciton line. there's an avoided crossing that has to appear. And it appears, and you have a lower polariton and an upper polariton appearing. Those describe the exciton and photon oscillating between each other and propagating in the material. Okay, so far so good. But let me advocate how to treat this state. Let's create a 2 by 2 Hamiltonian that treats photons and excitons side by side. Tau z equals 1 will be an exciton, tau z minus 1 will be a photon. It's like a spin. And this Hamiltonian up to a independent in the exciton photon space shift looks like this. There's an energy difference between exciton and photon times tau z. And there's a matrix element that connects them because they're both bosons, they can hybridize. That matrix element is a complex number that's a function of momentum. And there's a question, what does this complex number do on the ring of resonance? So what is the, so here's the lower polariton band. In this tau space, we start off with an exciton. Sorry, we start off with a photon. We end up with an exciton. So we start off with a -1. We end up with a +1. Now the only question is, what happens as we look at the ring of resonance to this hybridization, to this G? Well, what is this G? It is just, I didn't write the matrix element here, I guess, because I was supposed to keep the number of equations down. But this G is just a matrix element between an electron in the valence band and an electron in the conduction band, right? The matrix element that creates an exciton. It's the same G that we had before. So if that G can be arranged to wind, and this would be arranged because of spin-orbit coupling in the underlying material, we would have a lower polariton band that's topological. Now, in fact, you need another component with that. You also need, so this is a bit for the expert. If you want to see topological bands, you want to see edge states. You want to see edge states in the gap so that they cannot hybridize with any stuff in the bulk. Here, that would not happen. The edge states will appear somewhere here, but they can always hybridize with bulk states. So if we add an additional periodic potential, as you see here, we can separate the bands more and produce gaps where edge states can live in. We also need time reversal symmetry breaking in the form of a magnetic field. That will work. Now, in principle, I should spend a few more slides saying what's necessary for the space to emerge. I don't need to do that anymore. It's actually experimentally found. So Moti Segev's group, together with the Würzburg group, actually saw this happen. And I think indium arsenide wells arranged in this honeycomb lattice. And you can see a dispersion without a magnetic field. With a magnetic field, you see gaps open and these edge states emerge. And this is what it looks like in experiment. You inject light in one place and it propagates along the edge, not disappearing into the bulk. So it looks like it works. That's the Topolariton story. Now, maybe I can use my last few minutes. So first to ask any questions about the Polariton story.
Is it what literally happens? You illuminate a little piece of material and you see light propagate along the edge?
Well, so let me be careful because I'm a theorist. So what you see is light coming out of the edge. So the polaritons are allowed to escape. And you see where they come from because you see the light. But they only escape from the edge.
So it's really the edge of some material which was illuminated.
Yeah, material.
Oh, really?
I mean, I'm guessing this is like Blender, but that's the material. It's a computer image, but of the real thing.
So escape means you get electron-hole recombination. Is that what happens? And you get light emission. Is that the picture?
I think so. I mean,
yeah.
So there's always these two ways of solving for polaritons, right? You can solve like what I did, a Hamiltonian for electrons and photons, or you can look at the Maxwell equations with the electric function that encodes the electronic physics. I think you can do it both ways. But here they really looked at the polariton spectrum. Yeah.
Can you just clarify a moment again? What's happening as we go from figure B to C in the top right?
Magnetic field.
Oh, sure, on the magnetic field.
No, magnetic field. So this is a band structure that looks evocative of graphene. When you turn on the magnetic field, it looks evocative of a Haldane model. Looks like a topological insulator with dead states showing up.
Yeah. So the energy scales here are really large. Does this happen at room temperature or is this a low temperature scale?
That's a good question.
It looks like it should be a room temperature scale.
I think it could be. Yeah. You know, I didn't think about it because I think it's room temperature. Yes.
I guess the gap is 0.1 MeV, right? So.
No, but these are bosons, so you don't ask about the thermal states. You just ask about the.
The light probably is red because it's exothermic.
Yeah, the light is. Yeah, you did right away for it. Yeah, room temperature. This is not a dilution fridge, that's for sure. No, it's room temperature. Why am I wondering? Because all this physics is usually low energy for electrons. Exciton energies are very high.
Can I ask you one more practical question? What is the periodicity that's implanted into the material? What scale is that at?
You can kind of read it up here.
Oh, I see. That's from the wave vector. Okay.
Yeah, those are dots.
So it's microns.
Micron. It's dots. This is an engineering material. Yeah. Other questions? Yeah, actually, all the information is here, right? Red light. All right, so to finish, let me cram all the stuff that I do nowadays into the last 5 minutes. Bear with me. So far we're talking about doing things with a periodic drive. It's kind of fun, but it's limited. I wanted to show you how this periodic drives can actually give you new paradigms for controlling photonic states. So instead of thinking about periodic drives as just changing the Hamiltonian, it turns out that you can think about a periodic drive as adding dimensions to your system. So making synthetic dimensions. I wanted to have a meme for this, but I couldn't really find a good meme. So the best that I could do is hark back to my childhood and think about this show, Time Tunnel. I think most of you were not born when it was already banned from existence. So I think that Time Tunnel was you go into it and then you move in time. So it's like periodic structures in space make you move in time. I want to say the opposite. The periodic structures in time make you feel like you're moving in space. But you know, that's as good as I could get it. And so it was a good show. It was in black and white. So what I showed you before was false color. But you know, it had all this Cold War era electronics in it and the people sleeping by the phone. Anyway, so this is the idea of synthetic dimensions. And those give rise to new control paradigms. So let me tell you how it works. So let's start again with periodic drives. You have a simple Hamiltonian that has, think about spin half. It has a constant piece, also a piece that looks like cosine omega t. But let's be in the limit of a slow drive, namely small omega compared to the bandwidth of the Hamiltonian. So far we were in the opposite limit of fast drive relative to the Hamiltonian. Now in the slow drive, if I want to solve for dynamics, I can just take a wave function and expand it to the harmonics of the drive. Nothing prevents me from doing that. I am not assuming anything about this psi of t. I'm not saying they're constant, I'm not saying they're slow, I'm not saying anything. I'm just writing a wave function like this. I have the right to. Might be more complicated than not. But if I write it like that, I can put it back into the Hamiltonian, into time-dependent Schrödinger equation, and collect harmonics of the same number. And what this gives me is a connection between psi n and its neighbors. So this looks like a nearest neighbor hopping lattice. Looks like this, where n, the spatial dimension, is really just the number of photons that the system took from the drive. And this is like a tight binding model. You have to pay a price because when you take photons from the drive, you have to take in the energy. So it's one-dimensional system, but on a slope. That's the idea of synthetic dimension, and there are many great people who are thinking about this before me over the past decade. All right, so one drive, one dimension. Can we do it with more dimensions? Why not? How about we put two incommensurate drives, cosine omega 1, cosine omega 2t. I can always take the wave function for any system that lives in this potential expand it in the harmonics, n1 and n2. I don't want to write time-dependent Schrodinger equation. It's not that it's hard, it's just long, but it'll end up with a tight binding model in these two dimensions, n1 and n2, number of photons from drive 1, number of photons from drive 2. And the slope is now in the direction of a vector omega, omega 1, omega 2. So it's a sloped surface, but 2D. If those two frequencies are commensurate, rational to each other, it'll just be like a carbon nanotube. It will wrap on itself as compact space. Now notice, this is a driven Hamiltonian I'm describing. We often are told that driven Hamiltonians do not conserve energy. Not true. Everything conserves energy. So in this case, because of the finite bandwidth of the Hamiltonian, the system will be forced to live on a strip because it cannot take or give more energy than its bandwidth to the light. So the only motion in this space have to be perpendicular to this omega, just like Bloch oscillations, localizing in the direction of a force in any crystal. But there's a question, what is the motion over there? Now I'll show you how I can take this zero-dimensional driven spin and make it into a two-dimensional topological insulator. So let me take the Bernoulli-Hughes-Jang Hamiltonian, sine px, sine py, cosine px, cosine py in the sigma x, sigma y direction and sigma z direction. But now every time I see a px, I'm going to write omega 1t. Every time I see a py, I'll write omega 2t. This is as if the momentum is the phase of the drive, px the phase of one drive, py the phase of the other drive. And lo and behold, what is this? It's just a spin half driven by two elliptically polarized beams. But what do I get from that? The anomalous Hall conductivity actually makes this into a frequency converter. So one beam will come out weaker, one beam will come out stronger as a result. That's what I wanted to show you quickly. All right, so again, going back to this animation. But now, so what do I want? I should stop, but do I have maybe another 2-3 minutes? Okay. So, see if I can get this going. So, no. This is not the way to go. There's a way somewhere here. Like this. There we go. Okay, so how does it work? So again, px and py, phase of drive 1, phase of drive 2. This is like having a particle in a two-dimensional band that's driven by this force that pulls you through the Brillouin zone. Now every time that the particle goes through high Berry curvature, it's going to move perpendicular to omega in one direction. But what is this motion? We lose n1 photons, we gain n2 photons. One beam does work on the spin, the other beam receives that work because the spin on its own cannot retain work. The whole conductivity dictates that, okay, so d1 dt is dn1 dt times omega 1, same for 2, but now dn dt is cross of omega and the Berry curvature that we have in the underlying model, in the underlying two-dimensional electronic band. That means that averaged over a cycle, the work done by one beam on the other is quantized to be the Chern number of the underlying model over 2 pi times the product of the frequencies, the product of the angular frequencies. That's topological frequency conversion. So this was done together with Ivar Martin and Bert Halperin. And we were lucky to have Frederick Nathan join. And he worked out over the last 2 years whether you can use Weil semimetals as the spin for this. So Weil semimetals have a Hamiltonian, so it kind of looks like this out of the box. For each electron, a Weil semimetal has a Weil node, which has sigma dot momentum. But then if you couple that to light through minimal coupling, it becomes sigma dot P minus EA. And if you can make A to be these two beams of elliptically polarized light, every electron in the valence semimetal realizes the spin that's being doubly driven. If you do that, so here's Frederick and Ivar, my partners in crime on this. If you can do it, there's a new geometry that kind of emerges, which is kind of neat. So here's the dispersion and Fermi surface of vial nodes. We're hole doped. So here's the Fermi surface. Electrons are down below. It has to be tilted because electrons are like ants. Each electron will pump in different direction. You want to make sure that they all pump in an average direction rather than cancel each other. The tilt of the dispersion will do that. Turns out that the doubly driven electron in 3D momentum space, like that, will make the shape, will go on a trip around the Brillouin zone that looks like a bagel. But that bagel is a special bagel. Some people say Klein bagel or something. It has one orientation on one side and the opposite orientation on the other. It's like the sesame is on the outside over here and it goes on the inside over there. And the topological frequency conversion depends on whether the vial node is contained within the bagel or not. If it's not contained, no pumping. Contained on one side, on the sesame outside side, one directional pumping. On the opposite side, opposite directional pumping. You need to bias the band to get something finite. You get dissipation. You get dissipation because you can have a situation of the vial node actually sitting within the trajectory. That means that no matter what you do, the system is not adiabatic. And that's not good. So nature fights you with dissipation here. When everything is said and done, we had a crude model for the dissipation in this model that assumed that all relaxation processes have the same time. And we asked what that time needs to be in order we're having the vial semimetal with a frequency converter. And the answer was not so realistic, but not so bad. Around 200, 300 picoseconds. And the vial semimetal with the right property will become a monster frequency converter. Why do I say monster? Check out these numbers. Kilowatt per millimeter cubed. If you get it positive, it's really positive. And you can play games with matching the frequency. This is in the terahertz. Electric fields for this, not large, 10 to the 6 volts per meter, not so far from what you have in the microwave. You can play games with matching the frequency to the plasma frequency in the material to get extra amplification from a sub 1, the electric constant. That's where we stand now. Maybe this is the time to stop. So I was showing you that you can get new control paradigms for topological phases, go all the way to new control paradigms for photons. Maybe get a different kind of nonlinear amplifier from this topology. Thank you, and thanks for letting me speak to you. And I just want to say, I forgot to acknowledge my collaborators over here. That was due to Torsten Kartzig and Charles Gordine.